Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In today's lecture, we will not discuss any new quantum mechanical system or its solution. Rather, what we would do is that we would introduce a new notation that is extremely useful in formulating quantum mechanical problems. In fact, using this new notation, we could discuss all the previous problems that we had or we have discussed over the past several videos, and then we can see how advantageous the new notation is. The notation that we are going to discuss is popularly known as Dirac's bracket notation. Before discussing about this particular notation, let us see how this comes into play. Suppose we have a vector in the 3-dimensional space in the familiar Cartesian coordinate we are used to. Suppose we say that okay, there is this vector A which is given by A1, A2, A3 at the 3 coordinates. So, the way we write this vector as A is we define some unit vector along x axis, y axis or z axis. So, instead of keeping it specific to Cartesian, I am trying to keep it very general. So, therefore, I define one unit vector E1 along which my amplitude is A1. Similarly, I have E2, the unit vector. So, here E1, E2, E3 are the 3 unit vectors if we are discussing for a 3-dimensional space. In other words, I can write this I goes from 1 to 3 EI AI. So, these EIs, they are called the basis vector or unit vector. These basis vectors form a complete basis. What do I mean by complete basis? That means using these EIs, that is E1, E2, E3, I can define any other vector in this 3-dimensional space. So, I just need E1, E2 and E3 and then I can express any vector. So, that is why I call these EIs as forming a complete set of basis vectors. Now, this is about the Cartesian coordinate or you can take that to spherical polar coordinates, but when I translate this to quantum mechanical system, I have another problem. The problem is that in quantum mechanical system, I do not necessarily discuss about this 3-dimensional vector. Rather, what I need is that, as if you remember, most of the quantum mechanical problems that we have solved, the results, the eigenfunctions turned out to be a complete series of eigenfunctions. So, there are many number of eigenfunctions that come out of this solution of any quantum mechanical problem, because we see that the Hamiltonian is a Hermitian operator, and when I solve this Hermitian operator, I get a complete set of eigenfunctions. Now, the state of the system can be described as either one of these eigenfunctions or a linear combination of these eigenfunctions, because these eigenfunctions are a complete set. So, any arbitrary function I can use by expressing this arbitrary function in terms of these eigenfunctions of the Hermitian operator. So, therefore, I am dealing with, in quantum mechanical system, I am dealing with some n-dimensional space. What are these n dimensions? They are simply the n number of eigenfunctions that I can already get. So, when I say n-dimensional space in quantum mechanical system, I do not necessarily mean either Cartesian or spherical polar or any other coordinate system. What I mean is that the solution of the problem has n number of eigenfunctions, so that the state of the system can be expressed as a linear combination of this n number of eigenfunctions. So, therefore, the state of the system, like in the Cartesian coordinate, the position of the particle, and similarly in the quantum mechanical language, the state of the system is described by this n number of eigenfunctions. So, therefore, we require the definition for n-dimensional space. So, to continue our discussion in the same way, we in quantum mechanical systems, we define, since we have 1, 2, 3, so on so forth, n number of states. So, we define state I and we call them as the ket vectors or simply the kets. We call this ket, which are similar to this unit vector in the coordinate system. Using this I, so here I goes from 1, 2, 3, 4 up to n, I can define now the state of any quantum mechanical system, any arbitrary state of the system. Suppose I define this A and now I define this state, instead of as a vector, I am calling it as a ket, and I define this ket function as a linear combination of these ket vectors I multiplied by this A i's, which are simply the amplitudes along that particular dimension. So, now what I have defined is, this is known as the ket. Now, this ket function can also be expressed in terms of a matrix. For example, I can define a matrix A whose this matrix is essentially a column vector whose elements are simply A1, A2 and up till A n. So, you see, when I define this A as a column vector where each element becomes A1, A2, A n, this is similar to what I am expressing as a linear combination of this ket vectors i's. So, this simply says A1 is the amplitude along first dimension and so on so forth. Now, when I have defined this matrix A, similarly I can define the adjoint of this matrix, since this is a column vector. So, I can define this adjoint of this column vector, which will actually be a row vector, whose elements will be A1 star, that is the complex conjugate of A1, A2 star, A3 star and so on until A n star. So, now I have this column vector A, which is given as the ket, and correspondingly I have defined an adjoint of this column vector, which is now a row vector with A1 star till A n star as the elements in this. Now, this adjoint of A I define, I have called this A as ket, I define this as a bra function and I note it like this, where A, this is the bra function. Please note the sign. So, you have a vertical line in the left, the angle in the right, and here angle in the left and the vertical line in the left, and we have this, we are defining this as the bra. And how can we express this? We can express this simply as so, this bra function is expressed again in terms of the ket vectors I, but they are written in as their corresponding bra, and A I star, which is actually the complex conjugate of A I. So, now what I have is that I have a bra function, I have a ket. So, this together we see this is what Dirac proposed. So, bra and ket together we call this bracket. This also would resemble your regular bracket with a C missing. Now, we would see what we get when we actually, this is how we defined our bra function, bra and ket. Let us say we try to get a product of a scalar product of a bra and a ket. So, I have a bra here, I have a ket here, I am trying to get a scalar product of them. So, I can equivalently write, instead of these two lines separately, I can write in this notation. When I do this, you see this, the bra side would be a row vector with complex conjugate quantity, and the ket is a column vector. Now it is B1, B2, Bn. So, in the previous slide I defined the ket vector in terms of A. Now, I am defining this ket vector B whose elements are B1, B2, Bn, but it is still a column vector. Now, what I see is that I can multiply this. When I take this scalar product of these two matrices, I would get as A1 star B1 plus A2 star B2 and so on and so forth until An star Bn. In other words, I can simplify this as writing from I equals 1 to n Ai star Bi. So, this is what I should obtain when I take a scalar product of a bra and a ket. Now, alternatively, since I have already defined what are my the bra functions and the ket functions. So, let us express them in terms of the ket vectors I. So, this first I am dealing with the bra side. So, when I do this, I have I goes from 1 to n. So, this is my bra of A, which is A I star multiplied this bra function of corresponding to I. Now, I am interested, I will write down for the ket of B. So, when I write ket of B, just to keep the notation general, I introduce another index j, and I define my ket function B as a j into Bj. So, now you see what I have got is that I have sum over I j, A I star I j B j. So, now what I have done is that this bracket, the scalar product of two functions A and B, I am now expressing in terms of the scalar product of the unit vectors or the unit vectors in that space. So, I have this I j, and now look at the first line and the second line are essentially equal. So, when I look at the result from the first line, this one, and compare over here, what do I see? So, I would see for general value of, in this case I am seeing that I will have a summation for A I star B I, but here I have A I star and B j. So, here I would have only n number of terms, but if I here for all general values of I and j, I will have greater number of terms in this summation. So, what is the difference here? The difference is here is that my this I j must vanish for every value where I is not equal to j, and I j, this one should be equal to 1 for every for whenever I equals j. So, what the condition that I require to make this term and this term equal is that I j should be 1 when I equals j and should be 0 when I is not equal to j. And we know this when how to express this. This is simply we write as delta I j. So, the Kronecker delta function. So, where I equals j, this will become 1, otherwise it is 0. So, now what we see, if we consider this I j overlap as Kronecker delta, then I see this would become I star B I delta I j. So, now what I am telling is what I obtained is that these unit vectors i's are actually orthonormal. So, this we have already seen, but we are now redefining them in this vector in this bracket notation. Do you remember how we defined our orthonormal functions? Suppose we had psi I and psi j, we wanted to check whether they are orthonormal or not. This is how we would write. So, now this psi I star psi j has been can be replaced as psi I psi j, or alternatively simply I j. Now, you see that we have defined these overlap integrals in terms of bracket. So, we have bra, we have ket, together we call them the bracket. Okay. So, now we discuss one more interesting property from here. Suppose when instead of overlap of A B, let us say I am doing this overlap of A. What would I get? I would simply replace B I as A I, because both bra and ket have A. So, in this case I goes from 1 to n, A I star A I, which is now we see what are A I mod square. So, they are always going to be real quantities, because I am multiplying A I with A I star. So, this is again something that we are very familiar with. So, we are rewriting the quantum mechanical postulate in terms of the bracket notation. The important thing that is still missing from our discussion is that what are these AIs, because we see that if we have this, we have defined our ij as the unit vector, as the unit vectors, and corresponding to I function I ket, I have the amplitude as A1. So, now let us find out how can I get A1, A2 and so on. So, to do this we will do a little exercise. Suppose, so we have defined our vector ket as this one over here. Now, let us multiply a bra function j on both left hand side and right hand side. When I do this, in the right hand side, sorry, this is A I. So, I have A ket is defined as the linear combination of these terms, and so I am multiplying j in the bra from the left hand side on both from I am multiplying this from the left hand side, both in the left hand side and the right hand side of terms. So, I have this term over here, but now I see that j I are orthonormal functions. So, when they are orthonormal functions, so I have a summation over here, but I see in this summation only one term will survive, and that term will be when I equals j. All other terms will become 0. So, therefore, I am left with one term where I equals j, and that is when I is equal to j. So, that this term delta I j becomes 1. So, I am left with a j. So, now what do I see? A j, the coefficient, is actually the overlap of j function with the state of the system. This is also something we had known, how to get the amplitude of in a linear series expansion. So, again we are expressing this in terms of the bracket notation. We would do the same thing, but now we will define. So, instead of writing the ket, we will now define the bra. So, this is how we had defined bra. Now, instead of multiplying j in the left hand side, we will multiply j from the right hand side on both left and right side. So, when I do this, you would see defined as the bra part of the I. So, when I multiply j from left hand side, again I have a summation over many terms, but only one term will survive, that is when I equals j, and that will be a j star. So, I see this expression j of a gives me a j, and a and j in this way writing it gives me the complex conjugate of it. So, this would suggest that a j is essentially. So, when I am writing something in the bra and in the ket, if I exchange them, then I have this complex conjugate. So, in other words, so this is my m n, and I want to write as n m star. So, what we would do is that I essentially have psi m psi n star psi m. So, now this is the integral way of writing and this is the bracket notation of writing. We would look for one more important property that would that comes out from this discussion is that let us again write the ket. Now, what I have here in this ket definition, I have this a I term. I now know how do I get this amplitude a I. The answer to that is that I must overlap the ith function to the total ket. So, instead of a I am writing now because I know a I. So, because we saw that a j equals overlap of j function with the ket. So, similarly I am writing a I with a, but now when I look at the left hand side and right hand side, I see something very interesting is that from these two I can write that this term is equal to 1. Now, this way, so this is another way of writing 1. What does this tell me? This is possible, or this tells me that these i's form a complete set. So, this is the outcome of the fact that i's form a complete set. Now, what we are seeing is that these eigenfunctions, the given by this ket functions i's of a Hermitian operator, because we are dealing with let us say some operators which are Hermitian. In this case, we see that they form a complete set. They are the eigenfunctions, they are orthonormal, they are individually normalized as well as orthogonal. So, again we are deriving the properties of the quantum mechanical Hermitian operators in terms of this bracket notation. So, since we obtained quite a few information. So, to summarize, so this is what we have obtained. We went from basis vector notation to ket vector. Basis vector we defined in a Cartesian sense, and then we came to the ket vector which is now n dimensional. So, the ket vector A is defined in terms of these unit vectors I or the multiplied by a i's. So, the correspondingly the bra functions are given as in this relation. We also obtained that they are orthonormal, how the overlap a j equals j a star, and then we also saw that they form a complete set. Now, in our discussion so far, what we have missed is, or what we have not considered yet, is actually the operator. So far we have discussed the functions, the eigenfunctions. Now, what we would do is that we would introduce the operators to our discussion. So, these are the important rules that we derived in the previous part of our discussion, and now we will introduce this operator into this bracket notation. Let us see how we do this. Again, we will start our discussion from the Cartesian space that we are very familiar with. Suppose I have a vector A and I do some operation. So, I defined this vector as sum of ei's ai, where ei's are actually the basis vectors or the unit vectors along different dimension. So, now this is my vector A. I apply an operator A onto this vector, and this would simply take me and give me another vector. So, A goes to B when I apply operator A on this vector A. Now, if I see the action of operator A on this vector A, I would see that I would simply have to act A on this right hand side of the term. So, when I look here, I see that the action is essentially gives me this. What does it tell? So, these AIs are the coefficients that I know already how to obtain. Now, action of an operator A on this vector gives me this term. What is this term? This is action of operator A not on the vector A, rather one of these unit vectors EIs, but this is nonetheless is operation of an operator on a unit vector. So, this would again give me another vector. So, this is a vector. So, let us first see how can we express this new vector AEI. So, this is a vector. Now, this is a vector in the same Cartesian space. Now, I know that these EIs form a complete set. What does that mean? That means any arbitrary vector can be expressed in terms of these unit vectors. So, therefore, I have this new vector which is an arbitrary vector for my purpose. Now, I want to express it in terms of the unit vectors. So, I do this by taking a sum Ej, where Ej's are the unit vectors, and I give some value A and call them as Aji. So, now I have defined my action of operator A onto this EI and I obtained this. So, for example, if I do it for E1, what would I get? So, this is for all values of j, since we are talking about the Cartesian space. So, let us say we have j equals 1 to 3. So, you have Ej A j1. Similarly, action of A on E2 would give me Ej is the unit vector Aj2 and so on and so forth. So, let us look at what happens here A of E1. When I see here the new vector, when operator A acts on this unit vector E1, I see unit vector Ej and then some coefficients. How many are there? So, there are 3 in this case. So, for example, when A acts on E1, I need this A j1, that means j is 1. So, 1 1, A j as 2, 2 1, A 3 1. So, these 3 elements form a column vector that will express the action of operator A on this unit vector. Similarly, the action of operator A on the second unit vector would give me Aj2s. So, A1 2, A2 2, A3 2. So, this gives me another unit vector which comes from the action of A on E2. Similarly, action of A on E3 will give me. Now, when I see that together I have this Aj's, which is a 3 by 3 matrix, where the matrix elements essentially express the action of this operator on a vector A. So, what we have done is that in this new notation we can redefine our operator A in terms of some matrix elements Aj's. So, in today's lecture we discussed the useful bracket notation. We said that how we can define the state function in terms of these ket functions, and we also started discussing about how we can express operator in terms of this bracket notation. We will continue our discussion in the next lecture. Thank you for your attention.